Welcome to the fourth and last part of the essentials of the course Energy Supply for Buildings. This part is about the diverse energy conversion systems used to produce electricity. We will therefore address only the last column of this table describing the different ways of producing heat, cold and electricity. Heat and cold were addressed in part 3. Conventional electricity production is about fuel combustion, rotation and generators. If a wire of conductive material like copper moves within a magnetic field, it induces a flow of electrons in the wire, that is Faraday's law. A flow of electrons is electricity, and the electricity is then delivered to the grid. You see in the picture the magnet with its two poles, north and south, surrounding the coiled wire. The wire rotates and therefore moves, so electricity is induced. The voltage produced, V, is given by Faraday's law and depends on the velocity of the rotating coil, the length of the wire, the magnetic field B, and the angle between the wire and the magnetic field. This angle, theta, changes all time, creating a sinusoidal voltage, so-called AC, alternative current. Finally, the power obtained is the square of voltage divided by the resistance. The efficiency of such a generator is around 0.8. And of course, we need something to rotate the coil of wire. That is where our combusting gas and steam engines come. They are just meant as a way to rotate the coil. The basic idea is to use the kinetic and potential energy of gases or steam for rotation. Let's start with the first system, the combustion engine. In a combustion engine, fossil fuel or biogas is burned directly in the engine, making a piston move. The piston is connected to the rotor of the generator by a rod, and as the piston moves, it rotates the rotor. This is exactly the same principle as the gasoline or diesel motor of a car. When fossil fuels are used, all the fumes released to the outdoor air contain CO2 and harmful combustion products. In practice, the efficiency of such a combustion engine is between 0.35 and 0.45. So if we take a good engine with eta-conv 0.45, we end up with an overall efficiency for the production of electricity of 0.45 times 0.8, which is 0.36. In the combustion chamber itself, 45% of the higher heating value is converted to piston energy. The remaining part is lost through the hot exhaust gases and the rest hits the cylinder itself that must be cooled down. A heat exchanger is therefore placed around the cylinder, taking the heat away and releasing it to the environment, air, water, or much better, heating applications like district heating. In this case, we speak about cogeneration. The engine has produced at the same time electricity and useful heat. It is a so-called combined heat and power plant, CHP. Let's look now at turbine technology. The basic idea here is to connect a turbine to the coil's rotor. By injecting high-pressure gas in the turbine and to expand it towards lower pressure, the gas will impact the blades of the turbine with a high velocity, making it rotate. How do we get this high-pressure gas? Well, here too, that will be by burning a fuel in a boiler, generally gas, but also coal, liquid fuels, biofuels or hydrogen. But this time, by making use of the exhaust gases. The higher the pressure of the gas, the more energy it contains, so the combustion takes place at a high pressure and therefore also at a high temperature. You already know that air is needed for combustion, so the point here is first to compress air at a high pressure before injecting it to the combustion chamber. You see the compressor in yellow in the figure. Then the warm pressurized combustion exhaust gases are led to the turbine, where they expand, giving their energy to the turbine blades, which start rotating, driving at the right side the rotor of the generator and at the left side the rotor of the compressor. So, this compressor needs no electricity as it is powered by the turbine itself. The exhaust gases in the turbine are released to the atmosphere, that's the purple pipe below the turbine, with the CO2 and other harmful products they contain, if the fuel is a fossil fuel. Here too, green fuels can be used, like hydrogen. The conversion efficiency depends on the temperature levels, and as more than half of the rotor energy is used by the compressor, only half goes to the generator. In an optimistic case, eta conv, which is often called the turbine efficiency, is 0.45, which multiplied by the efficiency of the generator gives an overall electrical efficiency of 0.36. Here too, there may also be a heat exchanger placed at the exhaust side of the turbine. It can this way recover heat that can be used somewhere else, for instance for district heating, or to further preheat the compressed air before it comes into the combustion chamber. Let's switch now to the steam turbine. It is quite similar to the gas turbine, except that this time not the exhaust combustion gases are circulated, but steam produced with the boiler. You see that there is a heat exchanger in the boiler in which water is circulated and heated to high pressure steam. After expansion in the turbine, the steam is further condensed in a heat exchanger and the obtained water is pumped again to the heat exchanger in the boiler. The heat delivered in the heat exchanger is either lost in outdoor air or may be used in other applications like district heating. Let's look at the efficiency now. The efficiency of the boiler is high as usual, around 0.96. As the turbine is not connected to a compressor but only to the generator, we could expect it to have a higher efficiency eta conv than the gas turbine. However, the temperature of the steam and therefore the energy it contains is much less than in a gas turbine, so the blades rotate more slowly and less power is converted, resulting to a conversion efficiency of 0.5 at the best. So in the end we come here to a total efficiency of 0.4. There are also the so-called combined cycle gas turbines, which combines very efficiently a gas turbine with a steam turbine. The heat from the warm exhaust gas from the gas turbine is used instead of a boiler to produce steam for a second turbine. This way, two turbines are driven with one quantity of fuel instead of two, and two generators are producing electricity. The total efficiency of such a combined cycle is around 0.6. Most modern power plants use these combined cycles. Finally, a nuclear plant works exactly the same as a steam turbine, only the combustion chamber is replaced by a nuclear reactor and there is one heat exchanger more to make sure radioactive elements remain into the protective shell. The energy content of uranium is enormous and these nuclear plants deliver generally very large quantities of carbon-free electricity. Unfortunately, there is nuclear waste and risks due to radiation if control is lost on the reactor and after end of service life of the plant. We have just seen that a lot of heat is produced during the production of electricity. This heat is at temperature levels where it can be reused and it is a big pity not to use it. Such plants producing both electricity and heat are called CHP, combined heat and power. In an energy infrastructure that would be rational from the point of view of resource utilization and depletion, the reuse of waste heat should play an important role. This will be illustrated on the example of a fictive city of 100,000 households located in a moderate cold climate needing heating. We assume that on average each house has a heating demand of 15,000 kWh and an electricity demand for appliances and lighting of 3,500 kWh. In total, the city therefore asks for an annual 1,500 GWh heating and 350 GWh electricity for lighting and appliances. Let's look at scenario 1. The electricity is produced by a power plant using one of the combustion cycles to produce electricity with electrical efficiency 0.4, leading to the use of 875 GWh primary energy. The waste heat is just thrown away. The purple arrow indicates non-recoverable heat losses. In each house, condensing boilers are placed and we assume them to work in condensing mode with an efficiency of 0.96, leading to the use of 1563 gigawatt-hour primary energy, summing up to a total of 2438 annually. What would happen if we would now reuse the waste heat of the power plant to heat the houses and use electricity to power heat pumps? If you install heat pumps with an SCOP of 4 in 55% of the houses, an additional 203 gigawatt-hour electricity is needed, 0.54 times the annual heating demand divided by SCOP. So, the power plant needs to produce 350 plus 203 is 553 gigawatt-hour electricity. With an efficiency of 0.4, this brings us to 1383 gigawatt-hour primary energy. By using the produced waste heat, we can provide an additional 690 gigawatt-hour heating, by which the total heating demand is covered. In total, this leads to savings by 43% in comparison with the original scenario, which is in many countries unfortunately the current one. In climates where a lot of cooling is needed, similar considerations can be made, considering heat-driven absorption chillers instead of electricity-driven ones. Heat is a byproduct of electricity production, produced simultaneously with electricity. It is therefore logical to attribute waste heat no primary energy and no CO2 emissions. See method 1. That is done by several countries and is also meant to increase the use of waste heat and to reduce this way energy wastage. However, this can have adverse effects if power plants are oversized to produce enough heat while electricity would be thrown away. That's why there are also quite some countries in which the allocation of primary energy and CO2 emissions is done on the basis of the share of electricity and heat produced by 1 kilowatt-hour primary energy. See method 2. Next to waste heat from power plant, there are many other sources of local industrial heat that could be reused to heat buildings. They should be considered when designing an energy infrastructure. Also note that burning a fuel in a boiler just to make heat is a big waste of the potential of the fuel. It is much more logical to burn the fuel to make electricity and to use the produced waste heat for heating purposes. Let's look now at other ways of using turbines to produce electricity. It is again about generators rotated by turbines, but this time turbines without any combustion parts, using only renewable energy sources. As the energy source is fully renewable, the efficiency can be considered to be infinite and the primary energy and related CO2 emissions are zero. In a geothermal power plant, the steam comes directly from the ground. The temperature deep in the earth differs a lot depending on the location. In some places, steam at more than 200 degrees can be obtained, which is very convenient to power a turbine, like on the picture. So instead of using the steam for district heating application, it is this time used to produce electricity. Mostly, the system combines both at the same time and therefore is also a combined heat and power system. However, there are many other locations in the world where the ground temperature is much lower than 100 degrees, making it impossible to make steam with a pressure high enough to drive the turbine. This problem can be solved by using closed cycle, using a refrigerant with a boiling temperature lower than the one of water, a so-called organic Rankine cycle. Let's now look at how electricity can be made with the power of water. Hydropower. This is also turbine technology, but this time the turbine is powered by water flowing from a higher to a lower elevation. This can be done by using a simple run-of-the-river system which will produce electricity only when the flow rate of the river is large enough, or by storing water in a dam or reservoir in such a way that a continuous flow of water can be ensured. Those are the large hydropower plants. Tidal plants are working the same way, except that the direction of the water flow is changing with the tides. The maximum power that can be extracted is the potential energy of the water flow rate falling from height h1 to height ho. The overall efficiency of the turbine plus generator is high, around 95% for large plants and 80 to 85% for smaller ones. Let's go further and look at electricity from wind energy, see on the right. Here too, again, AC electricity is produced in a generator, which is driven by a turbine. The generator is placed in the box behind the blades, the nacelle, together with a gearbox in order to increase the rotation velocity of the generator coil. The electricity produced goes through electrical wiring along the shaft to the grid. In practice, approximately 27% of the energy contained in wind can be transmitted to the rotor. As the efficiency of the generator in these turbines is around 0.85, this brings us to an average electrical efficiency of around 23%. But that's not really a problem, as wind is fully renewable, its primary energy use is zero, as are its CO2 equivalent emissions. There are a lot of losses in such a wind turbine, but they cannot be recovered. Gone with the wind. So, combined heat and power is not possible. We touched on it in previous slides. Hydrogen, H2, is just a fuel among many others, and most boilers, combustion engines, gas turbines and steam turbines could be powered by hydrogen, with the giant advantage of no CO2 emissions during combustion, just because there are no carbon molecules at all. Of course, some changes must be made to the burners, but that is doable. However, there are much more clever applications of hydrogen than simply burning it for heat. Fuel cells are such an application. Fuel cells generate heat and electricity at the same time, just like conventional combined heat and power. How does a fuel cell work? Well, let's look first at step 1. A fuel cell is a bit like a battery. It consists of a platinum anode and a nickel cathode. In the middle there is an electrolyte which can transmit only positively charged ions. At the anode side, hydrogen is fed along the platinum, by which the hydrogen ionized, which means it is separated into hydrogen molecules which have a positive charge and electrons which have a negative charge. Electrons always have a negative charge. At the cathode side, oxygen from air is fed along the nickel, by which it ionizes, meaning it is separated into oxygen molecules which have a double negative charge. Obviously, there is an imbalance in charges here, meaning that this dissociation cannot be stable. We go now to step 2. There is this electrolyte solution in the middle that allows only positive charged ions like H+ to travel, while the oxygen ions are confined at the cathode as they cannot travel through the electrolyte. So the hydrogen ions that are very attracted by the negative ones travel to the cathode, which brings us to step 3, combining 2 positive hydrogen ions with 1 negative oxygen ion will bring the charges in balance, and that is called water, H2O. The reaction of formation of water is exothermic, meaning it produces heat that can be used to heat buildings directly or in district heating. And what happens with the electrons? They are all alone at the anode. There is therefore there an excess of negative charges, so the electrons want to move to establish a balance. The electrolyte solution is not conductive, so they travel through the wire, creating electricity. And this time there is no rotation of anything, so the current is direct current, DC, instead of being alternative. The direct use of hydrogen in combustion devices and in fuel cells may be very clean. Hydrogen is, like electricity, a secondary product, needing primary energy to be produced, and there may be CO2 emissions during its production. First, more than 90% of the actual production of hydrogen is based on fossil fuels and obtained by steam methane reforming, pyrolysis or oxidation. Let's be clear that this is not the type of hydrogen we would like to have. The same types of chemical processes can be applied on biomass to deliver hydrogen. This is already much better, assuming biomass is renewable. There are also a lot of advances in biological conversion, like fermentation or algae farms, in which algae produce hydrogen in bioreactors. And most important, hydrogen can also be produced by electrolysis. Electrolysis is the exact reverse reaction as in fuel cells. Instead of feeding hydrogen and oxygen to obtain water, electricity and heat, electricity is now used to split water into hydrogen and oxygen. Very clean production if the electricity used for this process is clean. And that is where it becomes interesting. This electrolysis could be used as storage for excess production of electricity by wind turbines or solar photovoltaics. When the electricity is not needed in the grid, it can be stored by transforming it into hydrogen in an electrolysis plant. The hydrogen can then be transported in pipes or containers to fuel cells plants, where it can be converted back to electricity. Of course, it is less efficient than just using directly the electricity, but it helps bridging the gap between electricity demand and electricity production by renewables. There is not always wind and not always sun. Photovoltaics, often abbreviated to PV, is completely different from solar thermal. It is the conversion of light into electricity using materials called semiconductors and the photoelectric effect. Look at picture 1 in this graphic. There are semiconductors which contain mainly negative charges, electrons, therefore, in yellow in the figure. They are called N semiconductors. There are also semiconductors which contain essentially positive charges in blue. We call them P semiconductors. Look now at picture 2. When you bring them together, something happens at the junction where negative and positive charges are attracted to each other, by which a kind of neutral and stable zone with as much negative as positive charges is built up, overlapping the junction. That is the white part on the picture. When solar radiation travels through the N semiconductor and hits the junction absorbs energy from the radiation, and this energy is just enough to help the electrons that are in the neutral zone close to the P side to jump further into the P side. This in turn allows the electron in the neutral part of the N side to jump to the P side to re-establish neutrality, which in turn gives the opportunity to the electrons above in the N semiconductor to move to the neutral zone. That's pictures 3 and 4. There is therefore a continuous flow of electrons from the N side to the P side, and if you put a conductive wire between both sides, the electron will take the shortest way through the wire and you get DC electricity. The efficiency of PV cells is defined as being the electrical output divided by the incoming solar radiation. Just like for other renewables, we will consider the primary energy to be zero, as well as the CO2 equivalent emissions. The actual efficiency of PV cells varies between 5 and 30%, 30 being really exceptional. Multicrystalline cells have an efficiency around 0.20 and monocrystalline cells around 24%. How to size PV cells in practice? Well, producers deliver in general data about the nominal power of their PV cells. This is expressed in watt peak. It is the maximum power of DC electricity a panel will deliver. Combined with equivalent full load hours for the location, this allows for a rapid estimation of the total annual electricity yield. For example, as a rule of thumb, the number of full load hours in the Netherlands is around 900, while in Mumbai it is around 2300. If we take the example of 1 square meter of panel with a peak power of 160 watt peak, this leads to a production of 144 kilowatt hour in the Netherlands and 268 in Mumbai. When using solar energy, we need to address the problem of intermittency, as solar radiation may be present when not needed and absent when needed. You see on this picture, in grey, the electrical demand of a large office building in the Netherlands in the month May. At night, there are still servers, some computers and lighting on, so the electricity demand is not zero. In orange, you see the electricity produced by 2000 square meters of PV cells. So, you see here that sometimes the PV cells produce more than needed, such as the orange part that does not cover the grey one. Sometimes it produces only a part of what is needed, such as the orange part overlapping the grey one. And there are also many hours where there is only a grey part. This electrical demand is not covered at all. Two parameters are used to characterize this phenomenon, the OEM and the OEF. The OEM is the on-site energy matching and is the fraction of electricity produced by the PV cells that can be directly used in the building, the orange-grey overlapping domain divided by the orange one. When the OEM is zero, the mismatch is complete and the electricity produced by PV should be sold to the grid or stored in batteries or just lost, which is a big pity. And when OEM is 1, all energy delivered by the PV cells can be used directly. The OEF is the on-site energy fraction and is the fraction of the needed electricity that is covered by the PV cells. In the graphic, it is the orange-grey overlapping domain divided by the grey one. When the OEF is 0, the mismatch is complete, and when OEF is 1, all electricity needed by the building is covered by the PV cells. In general, one should try to increase OEF and OEM as much as possible. This brings us to the end of this last lecture on the essentials of the course Energy Supply for Buildings. I hope this gives you inspiration to continue learning about buildings as sustainable energy systems. In the course itself, you'll learn more about each of the energy supply systems reviewed in this lecture. You will make comparisons between their performances and learn how to influence their performances and what that means for the design of heating and cooling systems in buildings. Goodbye and thank you for your attention.